Deep dive into sklearn, linear model, Lasso CV. The sklearn, linear model, Lasso CV class implements a Lasso model with iterative fitting along a regularization path using the least angle regression LAS algorithm, incorporating cross-validation to select the optimal regularization parameter alpha. This approach effectively finds the best model by balancing model complexity regularization with prediction accuracy. Let's explore the key aspects of this model. Understanding the basics. Lasso regression. Lasso least absolute shrinkage and selection operator is a linear regression technique that utilizes L1 regularization. This means that it penalizes the absolute values of the coefficients during model training, encouraging sparsity, driving some coefficients to zero. This promotes feature selection, identifying the most relevant variables for the prediction task. LAS algorithm. LAS is an efficient algorithm that computes the entire regularization path of a linear model, i.e., the solution for all possible values of the regularization parameter. It progressively adds features into the model, leading to a more efficient and interpretable path compared to traditional gradient descent methods. Parameters explained. Here's a breakdown of the Lasso CV parameters with detailed explanations. APES. Description: the machine precision used in the algorithm. This parameter controls the tolerance for convergence in the LAS procedure. Type float. Default 1 EO8. Impact: the smaller APES value results in a more precise solution, but may require more iterations for convergence. Max n alphas. Description: the maximum number of alpha values considered during the regularization path. Type int. Default 1000. Impact: the higher max n alphas value provides a denser regularization path, potentially leading to a more accurate selection of the optimal alpha, but at the cost of increased computational time. Normalize. Description determines whether to normalize the features before regression. If true, features are centered and scaled to unit norm. Type bool. Default false. Impact: normalization can improve performance when features have significantly different scales, potentially reducing the impact of outliers and improving the convergence of the algorithm. Precompute. Description controls precomputation of the gram matrix dot product of features. This can significantly improve performance when dealing with large datasets. Type true. False. Array-like. Default false. Impact: if true, the gram matrix is precomputed, potentially speeding up computations but using more memory. If an array-like value is provided, it is used as the precomputed gram matrix. CV. Description defines the cross-validation strategy used for alpha selection. It can be an integer for k-fold cross-validation, a CV generator, e.g., stratified k-fold, or non-default, which uses a default 5-fold cross-validation. Type int. CV generator. Default none. Impact: the choice of cross-validation method influences the stability and accuracy of the alpha selection process. Maxiter. Description: the maximum number of iterations allowed for the LAS algorithm. Type int. Default 500. Impact: if the algorithm does not converge within the maximum iterations, it stops and outputs a warning. Positive. Description restricts the model coefficients to be non-negative. Type bool. Default false. Impact: this parameter is useful when the coefficients are expected to be positive, ensuring a physically meaningful solution. Random state. Description: the seed for the random number generator used when shuffling the data for cross-validation. Type int. Default none. Impact: setting a random state value ensures reproducibility of the cross-validation results. Verbose. Description controls the verbosity of the output during model fitting. Type int. Default 0. Impact higher values provide more detailed logging information. N jobs. Description determines the number of CPU cores to use for parallel processing. Type int. Default none uses all available cores. Impact using multiple cores can significantly accelerate the model fitting process for large data sets. Refit. Description indicates whether to refit the model with the best alpha found on the entire dataset. After cross-validation. Type bool. Default true. Impact refitting on the whole dataset improves the final model's performance by incorporating information from all samples. Intercept scaling. Description scales the intercept term in the model. Type float. Default 1.0. Impact adjusting this parameter can sometimes improve model performance by balancing pay. Influence of the intercept term. Attributes. After training the model, the Lasso CV object exposes various attributes containing information about the model. Core. Description the estimated coefficients of the model. Type array like. Intercept. Description the intercept term of the model. Type float. Alpha. Description the best alpha value determined through cross-validation. Type float. Niter. Description the number of iterations performed for each alpha value during the Lasso algorithm. Type array like. MSE path. Description mean squared errors calculated for each alpha value along the regularization path. During cross-validation. Type array like. Alphas. Description the array of alpha values considered during the regularization path. Type array like. CV results. Description a dictionary containing results from cross-validation, including alphas, MSE path, ST-DERA path, and mean score path. Type dict. Methods. Fitx. Y trains the model using the given training data. PredictX makes predictions using the trained model. Score X. Y calculates the R2 score coefficient of determination of the model on the given data. Set paramsquarks sets the model parameters. Get paramsdeep true returns the parameters of the model. Example usage. Python. From sklearn, linear model import Lasso CV. From sklearn, datasets import make regression. From sklearn, model selection import train test split. Generate synthetic data. X. Y make regression samples 100. N features 10. Random state 42. Split into training and testing sets. X train. X test. Y train. Y test train test split X. Y. Test size 0.2. Random state 42. Initialize and train the Lasso CV model. Model Lasso CV CV5. Random state 42. Model. Fitx train. Y train. Make predictions. Y PRED model. PredictX test. Evaluate performance. Print FR2 score model. Scores test. Y test. Print F best alpha model. Alpha. Print F coefficients model. Core. Key advantages. Automatic alpha selection. Lasso CV automatically selects the optimal regularization parameter. Alpha using cross-validation, eliminating the need for manual parameter tuning. Efficient regularization path. The Lasso algorithm efficiently computes the regularization path, leading to fast and accurate model training. Sparsity and feature selection. Lasso regularization promotes sparsity in the model, effectively identifying the most relevant features for the prediction task. Considerations. Computational complexity. While Lasso is efficient, the computation of the regularization path might still be computationally expensive for very large data sets. Assumptions like other linear regression methods. Lasso CV assumes a linear relationship between features and the target variable. Conclusion. sklearn, linear model. Lasso CV is a powerful tool for fitting Lasso models with automatic alpha selection through cross-validation. Its efficiency and ability to identify relevant features make it a valuable choice for both model building and feature selection in various machine learning applications.